All right, so let's look at our stiffnesses, develop our stiffness matrix and load matrices for axial loaded members using the minimum total potential energy formulation. All right, so what we need to do to accomplish the minimum total potential energy is to look at the strain energy. All right, so the strain energy is we do an integration of over the volume of our stress times the strain over 2, and where V is our volume. From Hooke's law, we know we can substitute in for the stress our modulus times the strain, so then we get the modulus times strain squared. All right, so the total potential energy for a body in a closed system is the strain energy minus the external work that has been done. That's the total potential energy. So for a body with n elements, right, 1, 2, 3, in this case, m nodes, 1, 2, 3, 4, right, this becomes n, so E is equal to 1, so E is here, how many elements, so from 1 to n, total number of elements, and an I for our node numbers from node 1 up to node m. Right, generic form there. So the system will reach equilibrium where the potential energy is at its minimum. To find the minimum, we'll find the differential and set it equal to 0. All right, so we're going to differentiate our strain energy, differentiate our work, and set that to equal to 0 and figure out when that occurs. All right, so let's do that. So we got our equation here for the deflection in terms of our shape functions. All right. We need to get this into our strain energy equation. To do that, we need to look at, from mechanics of materials, remember that if the strain is the change in length over x, so what we're going to use is, in our case, the deflection over the change in y. All right, so let's do that. So we're going to differentiate our function here of the displacement and differentiate with respect to y, and that's why we're going to substitute in our shape functions, which have the terms y here and here. All right, so let's do that. So here's the differentiation. We're going to substitute in for u. Here's our u function. And differentiate with that with respect to y. All right, after we put in the shape functions. All right, so we put in the shape functions so we can differentiate with respect to y. And we do that and reduce. And we come up with the strain is equal to the negative of the deflection at node I plus the deflection at node j all over L. L being the length of our element. This may look familiar. Keep following along. You may have already guessed what's going on here. All right, so we're going to substitute back into our strain energy equation because we now have our strain in terms of something we can use here. That's going to remain constant. It's not a function of volume. So off the volume, it's going to be the cross-sectional area times the length of our element. So we substitute that in for the volume. Bring in our strain equation we just solved for in the previous slide. So minus ui plus uj over L. So we've got to square that. And squaring that out, we get our function here for the strain energy. All right, that all looks good. Now we need to minimize our strain energy. So again, we have to take the differential with respect to displacement. And we have two nodes. So we're going to have to do this both at node I, and we'll do it at node j here in the second half of the slide. So just looking at node I, we're going to differentiate with respect to node I. So this guy is going to go to 0, and then we'll have 2uj and 2ui left over there. So there are those guys, uj and ui. All right, get the 2's cancel out. All right, so that's a reduced down form. I'll do it at node j. So now we're going to differentiate with respect to node j here, differentiate with respect to node j. So this guy is going to 2uj, there we got 2ui as a result of this differentiation, and that guy's going to go to 0. Right, so there we go. Again, the 2's get canceled out there, and we're left with our reduced form of ae over L, uj minus ui. All right, so that's our minimized strain energy there. Now let's look at our external work. So external work is just the force being applied to the node times the deflection at that node. And then we want to differentiate that with respect to u sub I. And in our first case, node I, it's going to be just the force at node I. And it would be the same thing for u at node j as well. All right, so if we put this in matrix form, all right, here's this is minimum total potential energy. So here's our functions from before. So we got strain energy differentiated with respect to UI, with respect to the deflection at node J. All right, and there are force functions, so just the one we have up here up top here at node I, and here's the one at node J, and equals our forces at node I and node J. All right, so we got to bring all those together. So look at the total minimum total potential energy equation in matrix form. So here's the total differentiation of the potential energy equation, or the minimization, sorry, of the total potential energy equation. We have our minimization of the strain energy, and we have our minimization of the force. All right, so substitute those in, equations from the previous slide. All right, hopefully this is looking real familiar right about now. So we said if K, i.e. spring constant, stiffness constant, we substitute in for A over L, then our stiffness equation becomes K times the matrix 1 minus 1 minus 1, 1, UI over UJ, or UI, UJ, the column matrix there, the forces, right? So we applied the minimum total potential energy function to axial members, and we found that they act in the same manner as trusses, which hopefully is not a surprise because the axial members were, at least the case we looked at was 2-force member, just like trusses were. And so we end up with the same results there. All right, so let's apply this to example. So we have 30 kips being applied up here at the node 4 on the 3rd floor, 20 kips on the 2nd floor, 10 kips from the 1st floor being applied at node 2, 10 feet spacing between each. We got a modulus of 30 times 10 to the 6th psi, and the area of cross-sectional area of 20 inches squared. So we're going to find the vertical displacements of each floor level and also look at the stress in each portion of the column. All right, so we'll start out with the element stiffness matrix, which we just derived, right? AE over L. All right, so we plug in our cross-sectional area modulus over L, L being 10 feet, and we got to make sure our units stay consistent, so multiply that times 12 to get that into inches. So we get 5 times 10 to the 6th pounds per inch. So plugging that back in, and we see that in our stiffness is in all these cases because the lengths are the same, the cross-sectional area is the same, the modulus is the same, so all these stiffness matrices are all the same. So this is the element stiffness matrix, local coordinates. Actually, it's in global coordinates. They're all aligned in this case, but it's the element version of that. We bring all those elements into our global stiffness matrix. So if we've seen how to apply that in the previous videos. We got our global force matrix, so the force being applied at node 1 is 0, and then we got our negative 10 kips, negative 20 kips, and negative 30 kips for force at node 4. Set up our matrix equation there. Apply a boundary condition. We know there's no deflection at node 1 because that's in contact with the ground, so we don't expect that to deflect at all. So we'll call that 0. So put 1 in that column, 0s in the rest. In this case, it was 1 anyway, but note that if it wasn't, we'd have to apply 1 there. So solving with MathCAD or MATLAB, we should come up with these deflections at our different nodes in our beam, or in our column, rather. All right, so let's look at our axial stresses now. So we've got the deflections. Let's go back and calculate the axial stress. So the axial stress is going to be the force over area, and that reduces to the modulus times the change in length based on the displacements at node I and J over L. So for element 1, we got the 30 times 10 to the 6th psi, the negative 0.014 inches that node J reflects in element 1, and 0 at node 1 doesn't move, and the overall length of 120 inches gives us negative 3,500 psi in compression. So the C is just put on there because we have a negative sign out front. That's why we can call it compression. So we knew that for element 2, and we see we have negative 2,500 psi in compression there, so a little bit less, and then for element 3, negative 1,500 psi in compression there. Let's then move on to a second example, or just extending the example we were just on. We got the same column, got the same loads, the same elements and nodes. Everything's the same except for All right. We have all the deflections that we have solved from before. What we're going to do now is we're going to find the deflection at node A. All right, so this is not one we actually solved for. We solved for 1, 2, 3, and 4, but not node A. So how are we going to get node A? The deflection node A. Well, we came up with that equation, right? The shape function is describe the shape of the deflection in our elements. So we just have to come back and apply those in this situation. All right, so let's do that. So here's our equation. So we have the deflection in some element is equal to the shape function at node I times the displacement at node I plus the shape function at node J times the deflection at node J. So let's put in those equations there for our shape functions. We put in our shape function equations. All right. And we're going to put in the actual values now. So we're looking at element 3, and that's made up of node J is node 4, and node I is node 3. So that's where those guys come from, and likewise J is 4 and I is 3. All right. So substituting our values there, the global y to get to node 4. So this is the global y, not the lowercase y within the element. It's the global y. So it's 360 inches to get to node 4, 240 inches to get to node 3. Again, we have the length of our elements here, 120 inches. 120 inches. And the deflections, these are what we saw for in the previous problem. So the deflection at node 3 is negative 0.024, and the deflection at node 4 is negative 0.03 inches. So now we just have to solve this problem out once we put in where we want to find it. So where is node A at? So node A is at 300 inches. In this case, it was halfway between, almost halfway between, oh no, halfway between nodes 3 and 4. So we plug in 300 inches there and 300 inches here. And now we can run the whole calculation and we come up with the deflection is negative 0.027 inches at node A. Now, this is a linear case, so you could probably say I could have just done the average between node 3 and node 4. And you're right, because it's linear, you could have just done the average between the two, and you would have gotten negative 0.027. But there's other cases where the shape function actually won't be linear, and it'll be helpful to have this set up to solve them. So I hope you enjoyed the presentation. Again, put any comments, questions below in that comments section of the video, and be happy to respond to those. We'll see you in the next video. Thanks.